Okay, so we're going to talk about a proof of Green's theorem. And let's just recall that Green's theorem is that you can relate this 2D area integral, which is of the form qx minus py, to this closed 1D line integral of our vector field. And of course, our vector field we called PQ, and so it's saying that the derivative of f is on the left-hand side, and then this is f on the right-hand side. So it's a two-dimensional version of the fundamental theorem of calculus. Now let's just see why it works. So what you do is you specialize to P0 and 0Q. If you can show it in each of these cases, then surely you can just add the results. So these are a lot easier to think about. And also, square, just a square domain. So here are for our curve C enclosing our region R. In general, it could be anything, but I'm saying let's specialize now to the very simple situation of the unit square. And I claim that's actually good enough. So if we're on the unit square, let's do the P0 case first. Let me just fix that 0. Okay, the P0, we can actually now explain why it's a minus p. Other than the fact that this quantity, it kills gradients, which is a good thing when we have a closed line integral. But let's see why we get minus p. So now let's evaluate that path integral. So f dot dr. So there's actually three curves, right? There's C1, there's C2, C3, and C4. So clearly, if I'm going to draw f in red arrow here, because f is just pointing in a horizontal direction. So actually f dot dr is equal to 0 along C2 and C4. So all we need to do is consider the C1 and C3 cases. So the C1 cases will have our integral of f dot dr. It'll be an integral from 0 to 1 of p of x and y equals 0 dx. Right, we're on the y equals 0 x-axis. And C3, the one above it, it'll be the integral from 1 to 0, right? Because we're starting at x equals 1 and we're ending at x equals 0. P of x, y equals 1 dx. And you don't have to do y equals 1. I'm just putting that there for clarity. So how about I just remove that and put 0 and 1. So now let's add these two things. So our integral is actually equal to the integral of C1 plus that over C3. Remember, C2 and C4 are 0. So we know it's the integral from 0 to 1 of px0 plus the integral from 1 to 0 of px1. Now let's flip the integral. Let's flip this. This is minus the integral from 0 to 1, right? So now we see where that minus sign comes from. Because now this is the integral from 0 to 1 of negative. Let's pull that negative sign all the way out. Px1 minus px0. So now we see what's going on. This is actually p evaluated from y equals 1 to y equals 0. So now we just apply the 1D fundamental theorem of calculus. So we see that there's a minus sign that comes out front. So this is exactly the right-hand side of Green's theorem, right? We have recovered that py term. And that minus sign, we see the reason for the minus sign is that the top curve points left. Remember, if we draw that square and we do the positive orientation, which is counterclockwise, then the top curve points left. That's why we have that minus sign. And because left gives you that negative sign. Okay, so you can see now how we do something similar in the Q case. So if we just quickly do the 0Q case, then I'm just going to redraw the square one more time, and I'm also going to draw the force in red. We see that the integral of I'm sorry, we don't need integral here. The dot product, f dot dr, is equal to 0 in the C1 and C3 cases. So that means our integral, it is just equal to a C2 plus a C4 component. So the C2 component, if we do f dot dr, we see it is now, remember dr is just dx dy, right? Because that's what r is. So you take the dot product with 0q, you get q dy from looks like 0 to 1. We do the same thing now with C4, and now it's the integral from 1 to 0 because we're starting from the top with a positive orientation, and we're going down to x equals to y equals 0. So, and let me just fill in what the x values are. For this C2, the x value is 1, and then we have y dy. And for C4, we have 0, 1. So now we again apply the fundamental theorem of calculus. We add an x integral. Oh, I'm sorry, I'm getting ahead of myself. So let's add these two terms. So the integral of C2 plus the integral of C4, that's the integral 0 to 1 of, looks like we have q of 1, comma y, and then we'll have this minus sign because we have that wrong integration limit. So minus q of 0 y dy. So now, of course, this is q of xy evaluated from x equals 0 to x equals 1. So we just now apply the 1D fundamental theorem of calculus. And of course, now we just have 0 to 1, 0 to 1, qx dy, dx dy. This is dA, and this is the integral over our region, so it's just what we want. So this is the right-hand side of Green's theorem. So how do we go from this to more general regions? There's a nice trick you can do, and this is, you can use piecewise approximation for this of the domain. So for example, let's do a rectangle. We did a square before. So first what you do is, I would say that rectangle, I'm going to split it now into two squares, not to scale. And I'm going to draw arrows. Sorry. I'm going to draw arrows on that extra side in the opposite directions. And the reason this works is that if we just isolate these two things, we have integrals going in different directions on the same point. I know it doesn't look like it's the same point because I drew them side by side, but really what's going on here is I'm taking this line, I'm integrating it up and I'm integrating it down so they cancel. So the up integral plus the down integral gives you 0. Okay, so so I'm saying is, if you evaluate the integral over this and the integral over that, you get it's the same thing as the integral over this. So now you apply Green's theorem, and so now you get an area integral of one square plus an area integral of another square, and really this is just the area integral over that rectangle. Okay, so now we can construct rectangles. We can go to even more general. So for example, if I want a circle, what I can do is I can approximate this by a Riemann sum or not a Riemann sum, just a piecewise approximation by rectangles. So for example, I'll just put a grid on here, and I will color in the squares where that circle appears. Okay, and as you refine the grid, this actually approaches the area of that circle. Okay, and we know from that Green's theorem will work on here. Because we know it works on squares. So really, there's not really much of a difference between general domains and squares. So you can be assured that Green's theorem works in general. Okay, we'll now get to examples of Green's theorem.